Alright, so in this lesson we're going to start looking at some basic circuits involving capacitors. So what happens when we put capacitors and connect them together in order to make a circuit? Are there some basic rules that we could use to describe capacitor circuits that look similar to basic rules we use to describe resistor circuits? The answer to that question is yes, there are a certain set of basic rules we could use to describe what happens with capacitors as compared to what happens with resistors. First one to discuss is capacitors that are in series. So here I have C1, C2, and C3, all in series with one another. And so the one thing that happens if we rearrange this equation, we get V is equal to Q over C. Now, the one thing that I know about voltage in a series circuit is that if I add up the voltages over all the elements in the circuit, I should end up with the total voltage of the circuit. So if I add up the voltage on C1, the voltage on C2, and the voltage on C3, I should end up with the total voltage in the circuit. What this allows me to do is it allows me to come up with a relationship for the capacitors. It's also worth pointing out that because current was the same through the circuit at all points in time, that would also mean the charge stored on all the capacitors is the same. If current is the same through C1, C2, and C3 at all the points in time, that means the amount of charge that passed through each one of those and got stored on each one of those also must be the same. So Q1, Q2, Q3 are all the same. So if we wanted to figure out what the equivalent capacitance is, what is kind of like the sum of the capacitance of the circuit, we could take V total equals V1 plus V2 plus V3 and plug in what V looks like. Q over C equivalent equals Q over C1 plus Q over C2 plus Q over C3. And divide everything by Q, and we get a relationship that looks like this for equivalent capacitance in a series circuit. So this looks similar to an equation we get for resistors, only dealing with resistors in a parallel circuit. So what effectively happens if you add more capacitors in a circuit is you effectively decrease the equivalent capacitance. If we think about why that is, probably the best conceptual reason or the best conceptual way to think about that is if you think about capacitance as area of the plates times epsilon naught divided by the distance between the plates, what happens as you add more capacitors is you increase the distance between the two plates. You make the distance larger and larger. That would have the effect of decreasing the capacitance of the circuit. Now if we look at capacitors in parallel, and we rearrange it for Q, the one thing we can point out is that the total charge stored in this circuit has to be equal to the charge on capacitor 1 plus the charge on capacitor 2 plus the charge on capacitor 3. The reason for that is the total current that would travel through this circuit would be current through path 1 plus current through path 2 plus current through path 3. And there's nothing that guarantees those three currents have to be the same. Now the voltage or the potential should be the same on all three capacitors. That's because, well, if you apply the loop rule, you have three closed loops where voltage must be the same in all three of those loops. So if we plug in the fact that Q total equals Q1 plus Q2 plus Q3, and we've solved the capacitance equation for Q, we could say Q equivalent times V equals C1 plus V plus C2 times V plus C3 times V, divide by V, and we get the equivalent capacitance is the sum of the capacitances of all the capacitors. This looks really exactly like the equivalent resistance formula, only resistance in series. So the thing to point out with capacitors in parallel and capacitors in series, how to do those equivalency formulas kind of look like the opposite of what resistors in series and resistors in parallel look like. Now if you think about this from the epsilon naught A over D formula for capacitance, what's effectively happening as you add more capacitors is you're effectively increasing the area that you can store charges. If you increase the area but keep D the same, you increase the capacitance. So let's do a quick problem, and let's say we have three capacitors and we want to know what the charge in each capacitor is, and they're going to be connected in series and how much energy is stored in the circuit. So the first thing I want to do to figure out the charge is I need to figure out the equivalent capacitance, because remember, charge is the same in all elements of the circuit. And so if I figure out what the equivalent capacitance is, I get the equivalent capacitance is 4/3 picofarads. So if I then plug that into the formula, charge equals C times V, I end up with really 16 picocoulombs. Remember that pico is times 10 to the negative 12th. So if I wanted to figure out the total energy stored in the circuit, the way I could do that is equivalent capacitance times voltage squared, and I get 96 picojoules is the total energy stored in the circuit. Now I've asked the same question with the same three capacitors, only what if I put them in series with one another? So Q equals CV, we know V is constant. So for the first one, it is 72 picocoulombs. For the second one, it is 24 picocoulombs. And for the third one, it is 144 picocoulombs. So that means that the total charge stored in this circuit in total is actually 240 picocoulombs. That is far larger than the 16 picocoulombs we were able to store when we had these three capacitors in series. Now if I calculate the energy, probably the best thing to do would be to calculate the energy of each one independently, since we know really the capacitance and the voltage. And we get 1440 picojoules is the total energy stored in this circuit. Well, if we go back to the previous circuit, 96 picojoules, that's not just a lot more energy, that is a ton more energy. In fact, it happens to be about 15 times more energy having these three capacitors in parallel versus capacitors in series. So the thing to point out with simple capacitor circuits is that there are some relationships with series and parallel circuits that are very simple circuits. They look very similar to our relationships with simple series and simple parallel resistor circuits. We're going to look at the next couple lessons is what if we start to mix resistors and capacitors together? What happens in those types of circuits?